Hey, welcome to part 2 of the SliderCrankForwardDyn video. I'm on page 2. What I've done is I've taken the free body diagram that we've already derived in part 1 of the video, and I'm just going to write the Newton's law equations. You can look at your separate sheet with the free body diagram on it. I have this here just to have it in front of me so I don't need to scroll around too much. We're going to write our three Newton's laws. Sum of the forces in the x direction is m AG2x in general. Now, right away we recognize that xg2 dot is vg2x. We're after first order equations after all. And then vg2x dot, that's acceleration. That's 1 over m2 times the sum of the forces. And those forces are, according to my free body diagram, I've got f12x to the left. That's going to be minus f12x. I've got an f32x to the right. So my sign convention for the free body diagram says I have that as plus f32x. If f32x is plus 10, it's to the right. If f12x is plus 10, it's to the left. Alright, so there's my second first order equation from the x dynamics. Sum of the forces in the y direction will be mag2y. Yg2 dot, that's the velocity of the center of gravity vertically. That'll be vg2y. And vg2y dot, that's going to be 1 over m2 times the sum of the forces in the vertical direction, minus f12y plus f32y minus m2g. And now finally the sum of the moments about g2, positive counterclockwise, that's going to be ig2 times theta2 double dot. Now theta2 dot is omega 2. Omega 2 dot is 1 over ig2 times sum of the moments. I've got t. I've got minus t fric a, which I know is b omega 2. I've got plus t fric b, because if it's positive it's counterclockwise. T fric b is b times omega 3 minus omega 2. I'll just make a little note up here that those two terms I just put in are actually t fric a and t fric b. And now I have the moments about the center of gravity due to the pin forces. I will have, now here it's worth reminding myself of which way theta2 is. This link is drawn in the first quadrant, so determining the signs for the moments is pretty easy. I'll have plus f32y times g2b2. If it's a vertical force, I need a horizontal moment arm, cos theta 2. I'll have minus f32x g2b2 sine theta 2. And let's see, f12x and f12y. I'll have minus f12x times a2g2 sine theta 2. And I'll get a positive moment from f12y. a2g2 cos theta 2. So now I have 6 first order ordinary differential equations. I have to write the spring forces, of course, in terms of the state variables. So if I just flip up to the first page again, at A, xa2 and ya2, they are the vertical and horizontal deflections of spring KSA. If I have a positive deflection of KSA in the x direction, the force is going to pull back to the left, so f12x is going to be plus kx. I've drawn F12y pulling downward. That's the direction of the spring force on A2 in the vertical direction if it deforms as shown. And the stretch in that spring is going to be YA2. So following what we did in the most recent lecture, I will write, let's see, F12x. That's going to be KSA times XSA. Because there's damping in parallel, I'll also have RSA times VSAX. Where XSA is XA2 minus XA1. And let's see, XA1 is 0. XA2, to get to A2 from the origin, I go over to G2 and I come back a little bit. So XG2, which is a state variable, minus A2G2 cos theta 2. And then the velocity of SA in the x direction is going to be the velocity of A2x minus the velocity of A1x. Velocity of A1x is 0. The velocity of A2x is going to be the derivative of XA2, which is VG2x plus A2G2 sine theta 2 dot. But instead of writing theta 2 dot, I'll write omega 2 because that's one of my state variables. So all these equations, if I code them in the right order, they're going to give me F12x. Now, in what order do I need to code them? I can't code them in this order. In fact, when I start numerical integration, what I'm going to have is I'm going to have the current values of my state variables. So the first thing I'm going to need to code is I'm going to need to define XA1 and XA2. And then I can define the spring deflection in the x direction. And then I'm going to need to define the velocities of A1 and A2 in the x direction. And then I'm going to have to write an expression for the spring extension velocity. And only after I've coded all those equations can I finally go back and write a line of code that defines F12x. So what I've written there, those little numbers, that's what I'll call the coding order for the equations. And it's only after you've coded all 5 of those equations that you can actually write this second differential equation. Because I need to have already defined F12x before I use it in a line of code. So when you look at the Matlab code that I post, pay very close attention to the order in which these equations are written. Okay, I can do a similar thing for, so I'll say similarly, I can define F12y. It's going to be KSA YSA plus RSA VSAY. Okay, now I don't know how far I need to go with this in terms of writing all these Newton's laws. I don't know if I really have to write out all the Newton's laws for length 3. I suspect at this point you'd be able to get the 6 first-order ordinary differential equations, which would have in them F43x, F43y, and so on. What I will do, though, is I'll just quickly go through defining the constraint forces, the F32x and y, and the 43x and y. I'll define the constraint forces on length 3. So I will do that for you. Okay, now, so let's define constraint forces at B and C. So at B then, and I'll do this in the order that I'd actually write them in code. So I go back to my schematic. The deflection of the spring at B in the x direction is going to be xb3 minus xb2. So the first thing I'll do down here is I'll write that xb3, that's going to be xg3 minus b3g3 cos theta 3. So I go over to point G3 and I come back along link 3 and I get to point B3. xb2, that's, I go over to point G2 and I continue on link 2 a distance B2 G2 cos theta 2. Alright, and now I can define the deflection of the spring at B. It's going to be xb3 minus xb2. If that's positive, that means that B3 is to the right of B2. That means that link 2 is going to be pulling to the left on link 3, so F32x is going to be positive kx. That's for the stiffness portion anyway. There's also a damping portion. So I'll say the velocity of B3 in the x direction, that's going to be the derivative of xb3. So that's vg3x plus b3g3 sine theta 3 omega 3. The velocity of B2 in the x direction, that'll be vg2x. And right now I'm differentiating that equation. So that'll be vg2x. I'm going to have minus b2g2 sine theta 2 dot, or omega 2. And now I can say that the velocity of the spring at B in the x direction is the velocity of B3 in the x direction minus the velocity of B2 in the x direction. Now I can say that F, let's see, I need the force of 3 on 2x. So the force of 3 on 2, to the left on link 3, to the right on link 2, that's going to be KSB XSB plus the damping term, which is RSB VSBX. Now I can just type the equations in that order in my Matlab function, and after that then I can write my Newton's laws, because when the Newton's law equations have F32x in them, the computer will know what that is. Now I don't think there's any real need for me to go through that again in detail for the pin forces down here at link C. Although I suppose it couldn't hurt. What's the x deflection of spring at C? It's going to be xg4 minus xc3. And the y deflection of this stiff spring at C is simply going to be yc3. Actually, that's kind of interesting. Let's go through that. Okay, so at point C, alright, the x deflection of the stiff spring at C is going to be xg4. This is from the slider block. That's already a state variable, so this is going to be a little easier. xg4 minus xc3. If that's positive, that means that the center of the block is to the right of point C3. It's going to pull to the right on link 3. Alright, let's see, what's xc3? To get to xc3, I need to go to G3, and I need to continue on a distance G3, C3, cos theta 3. And if I want to do velocity, the velocity of the stiff spring at C in the x direction, it's going to be the velocity of G4 in the x direction, which is a state variable, minus the derivative of xc3, so minus vg3x. minus the derivative of G3C3 cosine. The derivative of G3C3 cosine is going to be minus G3C3 sine theta 3 omega 3. I'm subtracting the negative, so I turn that into a positive. Alright, so I think that's right. Okay, so now I've skipped a couple of steps compared to when I just started out. But now we can write that what's that? F for 3x is going to be KSC XSC plus RSC VSCX. That's for the horizontal. Now for the vertical, the y stretch of the stiff spring at C is simply going to be YC3. I'll make a note here. The vertical stretch equals the height of C3 above the block center line. That's all it is. Alright, so YC3. To get YC3, I need to go YG3. Now here's the tricky one. Do I need to go plus or minus C3G3 sine theta 3? Let's go back and look at the schematic. Way back. Up a little more. Okay, so here's our schematic. Here's link 3. If theta 3 was drawn in the first quadrant, then this link would actually be up like that. And to get the height of C3, I'd go up to G3 plus G3C3 sine theta 3. If an equation works for a link in one quadrant, it should work for any quadrant. If I go up to G3 and then I add on G3C3 sine theta 3, notice that the sine of theta 3 is going to be negative, and I'm going to end up coming back down, which is what I'm supposed to do. So the equation I need is I need that YC3 is YG3 plus CG sine theta. This term's actually going to be negative, so it all works out. Now, the velocity of C3 in the y direction is the derivative of that, which is going to be VG3y, a state variable, plus C3 G3 cos theta 3 omega 3. So that's how that works. Now at this point, I'm going to leave you to look at the SliderCrank Matlab code. Okay, and the Matlab code it's based on the schematic that we've done here. Well, I guess I should write one more thing. I should write that F43Y downward is KSC YSC plus RSC VSC Y. And let's see, what's VSCY? VSCY is VC3Y. Alright, so here are our two constraint forces. Get those in the code prior to your Newton's laws. So Newton's laws for link 3, you're going to have some of the forces x, some of the forces y, and you're going to have the sum of the moments. I'm not going to go through that. What I am going to do, though, is I am going to do Newton's laws for the slider block, because they're somewhat interesting. Okay, so I'll make a note here in the thing that you'll ultimately print out. Newton's laws for link 3. Well, maybe I can just scroll them down. But I'll skip a few steps. We're going to have xg3 dot is vg3x, and the real Newton's law equation vg3x dot is going to be 1 over m3 times the sum of the forces in the x direction, which should be a minus f32x plus an f43x. In the y direction, yg3 dot is vg3y. vg3y dot is 1 over the mass times the sum of the forces in the y direction minus f32y minus m3g. And on link 3 on that free body diagram, all those forces end up being downward. So I have minus f43y. The dreaded moment equation, theta 3 dot is omega 3. Omega 3 dot is 1 over the inertia times the moments. If I go back and look at the free body diagram of link 3, I am going to see a minus T fric B. And if you recall, T fric B was defined as B times omega 3 minus omega 2. I'm going to have a positive, actually no, I'm sorry, I'm going to have a negative T fric C, so B omega 3. So there's T fric B, and here's T fric C. And then, of course, I've got the moments due to the pin forces. Link 3 was drawn in the fourth quadrant, so I've got to be careful. I believe I'm going to get a plus F32Y times a B3G3 cos theta 3. I should get a minus F43Y G3C3 cos theta 3. My 3's aren't very good. I should get a minus F43X G3C3 sine theta 3. And then the last one I should get a minus F32X, and the moment arm for that will be B3G3 sine theta 3. And all those algebraic signs should work out in the end. And then last but not least, Newton's laws for the slider. And these will only include x and y dynamics. Alright, so in the x direction, some of the forces in the x direction is going to be m times the acceleration of g4 in the x direction. So I have xg4 dot is vg4x. vg4x dot, the acceleration, is 1 over the mass. Now if you look back at your free body diagram, forces in the x direction, we had minus F43x already defined, minus the friction force, and I'll just write F fric here. We've already got a somewhat clumsy relationship for that with that absolute value and so on. I think those are the only two forces in the x direction. So for the y dynamics, now for the y dynamics, because we're not allowing our block to accelerate, the sum of the forces in the y direction is going to be 0. So we don't get any more differential equations here. We're going to get an algebraic relation for F14y. That's the critical normal force that we use for our friction. F14y up is going to equal F43y down plus M4G. Now can we write this equation in the code? Yes. We've already discussed how to write F43y in terms of the state variables. And M4G, that's known. So F14y we can define with this algebraic equation. Now we have to realize that we must code this. We must code this before we find the friction force. So you've got to code this static equation, then you're going to have to code your friction force, and then, and only then, can you code the Newton's law for Vg4x dot. So the order of this is important. If you get things out of order, Matlab will tell you that you've got some variables declared that are unknown or whatever. Alright, so with this, you should be able to look at the posted slider crank code and reverse engineer it. You'll see how I first in the function define all the constraint forces, and then I use those in Newton's law. Alright, thank you, good night.